Alright, so we're going to go through two examples of how to find the real zeros, and it's quite a long process, so I allowed a lot of room to do my work. We're going to go through the steps for finding the potential real zeros of a polynomial function. Okay? Step 1. Use the degree of the polynomial to find the maximum number of zeros. So step 1. The degree of this polynomial is 3. So that means there are at most 3 real zeros. Notice we are not talking about any complex zeros at this time, only real zeros. Step 2. Use Descartes' Rule of Signs to find the possible number of positive and negative zeros. This is where we use the sign change. So if we look at f of x, which is 3x to the third plus 8x squared minus 7x minus 12, we're going to look at the sign changes. Positive, positive, negative, negative, negative. So there's one sign variation. One sign variation of an f of x means I have one positive real zero, or 2 less than that. Well, 2 less than that would be negative, so that is not an option. So I must have one real positive zero. Now we find f of negative x. F of negative x is going to be 3 times negative x cubed plus 8 times negative x squared minus 7 times negative x minus 12. Well, 3, this negative would come out in front since it's an odd exponent, becomes negative 3 x to the third plus 8x squared plus 7x minus 12. So the number of sign variations I have here is one variation here and one more variation here. So I have 2. Since I have 2 variations, that means I could have up to 2 negative real zeros, or 2 less than that, which is 0 negative real zeros. Sorry about that. There we go. So again, I had 2 sign variations. Since I had 2 sign variations, I have up to 2 negative real zeros. Or I could have an even integer less than this. I could have 2 minus 2, which is 0 negative real zeros. So I'll either have 2 or 0 negative real zeros, but I know for sure I will have 1 positive real zero. And remember, I could have at most 3 real zeros, so it's possible to have 1 positive and 2 negative, because that totals 3. But I could also have 1 positive and no negatives, which means I only have 1 real zero, because I don't have to go all the way up to 3. Now that I know how many zeros I'm looking for and what signs they are, that will help me in determining or lessening the list of possible zeros that I have to play with. The third step up here now says, if the polynomial has integer coefficients, which it does, use the rational zeros theorem to identify those rational numbers that potentially could be zeros. So we're now going to find all of the potential zeros by finding P and Q. So first we find P. I believe we did this on the previous example already. The 3x to the third plus 8x squared minus 7x minus 12 was the previous example from the previous page, where we found the P and we found the Q, and we found that P over Q, my possible real zeros, was that long list of 18 possibilities, and I will write them out here because we've already done that math. Good. We have 18 possibilities. So I have to check all 18 of these zeros. One of them is going to be positive, and either 2 or 0 of them will be negative, and see if they work inside of this function as being a real 0. So how we do that is we just start plugging them in and finding them. I generally like to start with the easiest ones first, hoping that I hit something quickly, because once you find a 0, the next one becomes easier. So again, in order to determine, for example, if I want to test 1, let's test plus and minus 1 first. Okay, so let's plug in f of 1. If I plug in f of 1 up into this function, 3 times 1 is 3, plus 8 is 11, minus 7 is 4, minus 12 is negative 8. Hey, that's a remainder. And remember what we said, when there is a remainder, that means that x minus 1 is not a factor, which also means 1 is not a 0. So by finding that remainder, you can determine whether something is a factor and whether that actual number is a 0 of the polynomial. So I can now exclude the number 1 from this list. Let's try f of negative 1. If I plug in f of negative 1 here, I get negative 1 times 3, that's negative 3, plus 8, plus 7 minus 12, that's 5, plus 7 is 12 minus 12, oh, that's 0. So I have a 0 remainder. Since I have a 0 remainder, that means x plus 1 is a factor, which means negative 1 is a 0. So I have just proven a whole lot about this function by finding my first 0. And luckily I stumbled upon the first 0 really quickly. I didn't have to go too far into this list of potential zeros. So now, since I know it's a 0, what I can do is I can divide. So I'm going to divide. There's two ways we can divide. We can divide using long division, and then there's also something called synthetic division, which I'm going to show you now. So I'm going to now divide. Since I know this is a factor, I'm going to go ahead and divide this factor into the original polynomial to see what's left over. Since I know the remainder is 0, now I can do the actual division. So we're going to do the actual division. So x plus 1 is certainly going to divide into 3x to the third plus 8x squared minus 7x minus 12. So let's do the division. X divides into 3x to the third, 3x squared times, and when I multiply, I get 3x to the third plus 3x squared. Then we subtract this quantity, which leaves me with 5x squared. Bring down the negative 7x. X goes into 5x squared 5x times. So when I multiply, I get 5x squared plus 5x minus this quantity leaves me with negative 12x. Bring down the minus 12. X goes into negative 12x, negative 12 times, and when I multiply, I get negative 12x minus 12. And when I subtract this quantity, there is my remainder of 0. That is what I wanted. The remainder of 0 will match the remainder of 0 that I found that I knew I was going to get. So if I didn't get that here, I knew I did something wrong in the division. Now a shorter method of doing long division is also to do what's called synthetic division. If you'd like to use synthetic division, we take the actual 0, in this case, which is negative 1, and we just divide it using just the coefficients. So it's just a shorter way because you're not using all of the x's in here. I know this is to the third, to the second, to the first, and my constant. So you have to leave placeholders. So if there's no term, make sure you put a 0 in its spot. So again, it's just the placeholders of all of these coefficients. And out here I put the 0. So the first thing we do is we bring down the first term. And then we divide. We multiply. 3 times -1 is -3. And then we add. 5 times -2. Or excuse me, 5 times -1 is -5. And then we add. -12 times -1 is 12. And then we add. And that's my remainder. This is a much shorter way to do it. But if you're not familiar with synthetic division, you obviously can use Khan Academy or Google some videos to get a little bit better understanding of it, because it does save some time. So now that we've proven that the remainder is 0, the quotient that's left over, after I take this divisor out, the quotient that's left over is here. So in other words, the divisor times the quotient equals the polynomial we started with. Same thing here. The divisor times the quotient is going to equal the polynomial inside. So if I were to rewrite this, I know that x plus 1 times 3x squared plus 5x minus 12 is actually equal to the original polynomial that I started with, which was 3x to the third plus 8x squared minus 7x minus 12. So I have just figured out a way to factor this original polynomial with this large degree into something a little bit smaller and more manageable. Now, if you're good at factoring, you can continue to just factor this from here rather than going back up into all your zeros and finding another one from this list. You certainly can, but then you're going to have to do all this long division again. You have to guess at each one and do long division to find the other zeros. I like to think I'm a little good at factoring, so I'm going to try to factor this, which always will be the case. I know this is going to factor into 3x minus 4 and x plus 3. So this is going to be my fully factored form. Once you have your fully factored form, you can easily determine what your 3 zeros will be. So my 3 zeros are going to be at x equals -1. Well, we set this equal to 0. I add 4 and divide by 3. And this one says x is -3. So I have 3 zeros. These are my zeros at -1, 4/3, and -3. So I have 1 positive 0, and I have 2 negative zeros. And remember when we talked about that up here? We're going to have 1 positive real 0, and we're going to have up to 2 negative real zeros, and we just confirmed that. 1 positive and 2 negative. All right, so we're going to look at 2 more examples. All right, here we go. We've got another polynomial. This one is to the 3rd power. So the first step is to determine how many total zeros you might have up to. Since the degree is 3, that means I can have up to 3 real zeros. Now let's determine how many positive and negative zeros I'm going to have. The first thing I look at is the sign changes of f of x. Well, f of x is x to the 3rd plus 2x squared minus 5x minus 6. I have only one sign change, one variation of sign. That tells me I'm going to have one positive real 0. I could have 2 less than that, but that would be a negative, and that cannot be possible. So I absolutely will have at least one positive real 0. Now let's find f of negative x to determine the number of negative real zeros I might have. So now I plug in negative x. So negative x to the third plus 2 times negative x squared minus 5 times negative x minus 6. Well, that's equal to negative x to the third plus 2x squared plus 5x minus 6. I have one sign change here and another sign change here. So I have 2 variations. So that means I'm going to have 2 negative real zeros, or 2 less than that, which is 0 negative real zeros. All right, now step 3 is to find all potential zeros. So first we find P and Q. To find P, we look at all of the factors of the constant. This factors of negative 6. Factors of negative 6 is going to be 1, 2, 3, and 6. Factors of Q are going to be factors of the first coefficient, in this case is 1. So luckily I only have 1. Now we find P divided by Q. These are going to be all potential zeros. P divided by Q. So 1 divided by 1, 2 divided by 1, 3 divided by 1, 6 divided by 1. So this is a list of all potential zeros. All the zeros, which might be up to 3, they will all be found in this list. You will not find a 0 that is not in this list. So I only have to check 8 numbers, of which I'm only looking for 3. So this is a very doable exercise. So now we test some points. Let's look for the remainders to decide if we even have to do the division. So let's test the first point 1. I always start with the easiest. So let's test f of 1. If we plug that in, we have 1 to the third plus 2 times 1 squared minus 5 times 1 minus 6. That's 1 plus 2 is 3, minus 5 is negative 3, minus 6 is negative 9, or is it negative 8? 1 plus 2 is 3, 3 minus, it's negative 2, that's negative 8. That's a remainder. So, no, that is not a 0. Let's try f of negative 1. F of negative 1. Let's plug in negative 1 here. If I plug this in, I get negative 1 plus 2 is 1, plus 5 is 6, minus 6 is 0. Hey, I got a remainder of 0. That means this is a 0. This is a 0 right here. I didn't even have to go any deeper into my list. I didn't have to go all the way over here to 6. I found it right away. That's great. All right, so now I'm going to do the long division to find out what the quotient is after I divide this factor out. So I'm going to take that negative 1 on the outside. I again will show you synthetic division to show you what that looks like. So long division, we're going to take x plus 1 and divide it into the polynomial, which is x to the third plus 2x squared minus 5x minus 6. When we divide that in, we get 2x, excuse me, no, that's not right. X squared times x is x to the third. X squared times 1 is x squared. When I subtract, I get 1x squared, and I bring down the 5x. X divides into x squared x times. So when I multiply, I get x squared plus x. And then when I subtract, I get negative 6x, and I bring down the minus 6. X goes into negative x, negative 6 times. So I get negative 6x minus 6. And when I subtract, I get that remainder of 0 that I knew I was going to get up here. Okay? Or I can do synthetic division. If I do synthetic division right here, I take the actual 0, in this case is negative 1, and divide it into just the coefficients. So it's going to be 1, 2, negative 5, negative 6. And when I do synthetic division, I bring the first one down, I multiply and add, multiply and add, multiply and add. So there's my remainder. So I've definitely proven you don't have to do both of these ways. Most of you are going to like the synthetic division much better because it's faster if you can pick up on it. I've already learned what the quotient will be after I divide out this factor. So when I divide out the x plus 1 out of this polynomial, I'm left with x squared plus x minus 6, which you can obviously see in here too. X squared plus x minus 6. So then I can just finish factoring myself. Since I found the first factor, I can factor quadratics a lot easier. This is going to factor into a plus 3 and a minus 2, which means my zeros are going to be located at negative 1, negative 3, and 2. And look, all of those numbers are in my list right here. Negative 1, negative 3, and positive 2. And the signs also match. I said I'd have one positive, and I said I might have up to 2 negatives. So all of these details will point in the same direction. One more. Here we've got a polynomial. This time it's to the 4th degree. So since it's to the 4th degree, I might have up to 4 maximum real zeros. So I might have an additional real 0 than the last 2 examples. Now let's look at the sign changes to determine whether they are positive or negative. In the original function, f of x, how many sign changes do you see? Positive to negative, negative to positive, positive to negative. So that's 1, 2, 3 sign changes. So that means I have up to 3 positive real zeros, or 2 less than that, which is 1 positive real 0. Then we look at f of negative x. F of negative x is going to be negative x to the 4th minus negative x to the 3rd plus 2 times negative x squared minus 4 times negative x minus 8. This is a positive. This will become a positive. This becomes a positive. This becomes a positive minus 8. So I only have one sign change, which means I'll only have one negative real 0, or 2 less than that, which is not possible. So to find 4 maximum real zeros, I could have 3 positives and 1 negative, which equals 4, or 1 positive and 1 negative, which would be only 2 zeros, and that's okay. This is just the maximum number. So now we do the rational zeros theorem, the P and the Q, to determine what the zeros potentially are, and then we go and we find them all. So let's first find P and Q. P is going to be all of the factors of the constant. So P could be 1, 2, 4, and 8. Q is all of the factors of the coefficient in front of the first term, which is 1. So that narrows our list down quite a bit. So all potential zeros will come from the list of P divided by Q. So 1 divided by 1, 2 divided by 1, 4 divided by 1, 8 divided by 1. So this is a list of all potential zeros. And we're going to have to check all 8 of those zeros potentially to determine whether it's a zero or a factor of the original polynomial. So we're going to test some points. Again, I always start with the easiest, which is 1. So let's try f of 1. So we're going to plug f of 1 up in here, and we get 1 to the 4th minus 1 to the 3rd plus 2 times 1 squared minus 4 times 1 minus 8. So that's 1 minus 1, that's 0. 2 minus 4 is negative 2. Minus 8, that's negative 10. That's a remainder. Remainders will not yield zeros. Let's try f of negative 1. If I try f of negative 1, I plug in negative 1 into the function, and I have negative 1 to the 4th minus negative 1 to the 3rd plus 2 times negative 1 squared minus 4 times negative 1 minus 8. So this is positive 1 plus 1 is 2, plus 2 is 4, plus 4 is 8, minus 8 is 0. Hey, that gives me a remainder of 0. That will work. So that tells me negative 1 is one of the zeros. I have found one of the zeros, but there might be up to 3 more. So let's go ahead and do the division and see what's left after I take that out. I'm going to go ahead and do the synthetic division because I do think it's more expeditious. So we're going to take that negative 1 and we're going to divide it out from this polynomial. We'll just write the coefficients: 1, negative 1, 2, negative 4, and negative 8. So we bring down the first term, and then we multiply. Add, multiply, add, multiply, add, multiply, add, and there's my remainder. So that means this is my leftover polynomial, which gives me, that means the factor of x plus 1 was a factor, and what would be left over starting from the end? This would be the constant, x to the first, x squared, x to the third. So I have now factored the original polynomial up here is now equal to this factored form right here, which clearly I am not done. However, I might be able to factor this. I might need a separate piece of paper here. Let me grab that because I'm running out of room. So if I go to factor just this piece over here, let's see how that would get factored. Okay, so let's just look at this piece right here. So x to the third minus 2x squared plus 4x minus 8. Maybe I can group this. Let's try. Let's at least try to group. So if I took out an x squared, I'm left with x minus 2. If I took out a 4 from these two terms, I'm left with x minus 2. Oh, wait, I can group these. X squared plus 4 times x minus 2. So this is the factored form of this guy right here. So I'm going to write this as x plus 1 times x squared plus 4 times x minus 2. So this factors down into this factored form. Now at first glance I think, oh wait, this is factorable. But it actually is not because of that plus sign. This is the sum of two squares, which is prime. You cannot factor the sum of two squares. So this is completely factored form. So to find the zeros, we know the zeros are going to be located at -1 and 2, and there are no zeros from here. There is no way to make this ever become 0, because anything squared is positive, and when we add another positive number, you'll never get 0. So the only two zeros I have are -1 and 2. And we knew that that might be a possibility of only having one negative real zero and one positive real zero. So I have found the two real zeros down here. One last thing you could do if you wanted to check this with a graphing calculator is you could always graph this. I just want to give you one example of what a graph of this would look like. So if we look at this graph, and I plug all of this information in that's in this original polynomial, we would do x to the 4th power minus x to the 3rd power plus 2 x to the 2nd power minus 4x minus 8. And when I go to graph this, you're going to see that we will actually have two zeros, and they're going to be located at -1 and 2. And look right here. There's my zeros, -1 and 2.